Hey everyone, in today's video we're going to keep working with differential equations and we'll have a new way of kind of looking at them without actually solving them. That's called a slope field. So here's the deal. We said a differential equation is an equation where you're starting with the first derivative of something else, right? You're starting with dy dx or something else, something that measures the slope of something. Now, here's the deal. If you stick with mathematics, you're going to spend a lot of time learning how to solve different types of differential equations. I'm going to teach you how to solve 4 or 5 types in this class. If you take Calculus 3, or in high school it's called multivariable calculus, you'll learn how to solve them with a couple extra variables. Then, once you're finished with calculus, you know what the next class up in mathematics is called? Differential equations. So there's a whole lot to this field. Again, we're just going to scratch the surface here. What I'm going to teach you about today is what we can do to visualize a differential equation even if we can't solve it. So, and by solve it I mean anti-derive it. So here's the deal. We know that the differential equation gives us the slope of some other equation at every point. Again, because it's defined in terms of the first derivatives. That would be slope. So what I want you to do is to first, if we're going to construct a field here, I want you to evaluate what the slope of the solution would be if the solution went through these points. So basically what we're doing here is, what would the slope of y be if it went through these points? And it's as simple as, okay, we'll just plug the point into the differential equation because that gives you the slope. And then let's kind of sketch it. So like, it doesn't really matter where we start. I'm going to start, how about in the top left corner? I'm going to start with this point. So this point is -1 and then +2. If I plug this into our differential equation, I would do -1 plus 2, and I'd get a slope of +1. So I'd kind of draw, I'm just doing my best to draw a slope of 1, and this is just a thing I do. I find it helpful to scratch down the slope right next to it. Officially, if you're drawing a slope field, you don't need to write down the slope. You just got to draw what the slopes would look like. And then my advice is to either work column by column or row by row. It doesn't matter. Let's just go down the line for the row here. So this one would be 0, 2. If I plug that in, I'd have 0 plus 2. So my slope here would be 2. So it's just got to be a little bit steeper than our first one. And then here, this would be 1, 2. If I did 1 plus 2 to get my slope, well, that would be 3. So this would have to be a pretty steep line. And let's repeat that for every single point we have on the graph. So that's why I made the differential equation pretty straightforward. We're just adding the x and y values together. So over here I'd have -1 plus 1. So I'd have 0. So if the function went through here, it'd have a horizontal tangent. Let's see, this would be 0 plus 1, so we're back to a slope of 1, pretty gradual. This point's 1, 1, so 1 plus 1 is 2. Let's see, -1 plus 0, that'd be -1. So now I gotta draw it the other way. 0 plus 0 is, in fact, 0. Amazing. And 1 plus 0 is 1. Let's see, -1 plus -1, -2. -1, 0, -1. -1, +1, back to 0. And let's see, -1, -2. Okay, so we got a -3 over here, -2, and -1. Okay, doesn't really look like much, right? But you can kind of start to see, okay, hypothetically, if this point existed on the solution, okay, well I know it'd be sloped steeply up here, and it looks like as it moves off to the right, it would get more gradual as it goes as it moves left and down. Well, as I go left or as I go down, the slope gets smaller. So it gets smaller and smaller, and eventually somewhere over here I got to have a horizontal tangent. So at some point it's got to kind of level off. And then it looks like maybe if I follow it backwards, you know, I see some negative slopes over here, but then I also see it level off. So here's the deal. Again, the slope field is just there to help you try and kind of visualize what the solution would look like. It's not going to be perfect. And in our class, Calculus AB, we have kind of two jobs. We'll either be tasked with drawing a small picture of a slope field about this size, or honestly, maybe even a little bit smaller. Or if you flip over the next page, we'll be tasked with identifying, hey, which slope field, what is, like, actually go forward one more page. Like, here's 4 slope fields. A common AP multiple choice question is, hey, which of these slope fields matches the differential equation? Or another common AP question is, hey, here's a slope field. Which of the following could be its differential equation? So it's kind of the other way around. So I'll give you some tricks to kind of think about those identifying things. Drawing it, again, it's pretty easy. You just come up with the slope everywhere and plot that. It's kind of hard to graph these on the nSpire. Well, okay, it's not hard. It's just you got to press like 20 different buttons if you want to graph them on the nSpire. And I'll just tell you right now, the slope field questions never come up on the calculator portion of the AP exam. But if you want to check your work, you know, on your homework or something, let's go to Desmos. So I'm putting this Desmos link on today's date in Canvas just right underneath this video. And it's got a spot here where you can plug in your differential equation. So let's do that. And it'll draw the field from -10 to +10. So what was our one, the slope field we were just working with was x plus y. So I'll press enter. It takes a second. By the way, this will like use a lot of your computer's CPU because it's drawing a lot of lines. So like immediately it's using like 40% of my tablet's CPU, and you might hear the fan kick on. But if we zoom in just a little bit, it's kind of hard to zoom in on the tablet. Well, maybe we won't zoom in, huh? But if you look kind of at this inner box, that's what we were just drawing. And see how we have that diagonal line of the horizontal tangents. You'll also see on the calculator there's this little point that you can drag around. And it's a point where you can evaluate the slope anywhere. So if you just drag this around anywhere that's not even on like a whole number or something, it'll still show you the slope and how the function would kind of move. If it was going through that point. So, yeah. All right. Let's turn the page. All right. On our next page, like I said, we have 2 slope fields. We have 2 differential equations. Our job is to identify which one's which, because that's a common AP task. So, let's see. I see one of the differential equations. So they're both signs of something. I see one of them is the sign only of x, and the other one is a sign only of y. So kind of what I'm going to be looking for here is I'm going to be looking for, does one depend on y? Does one depend on y? Other on x? So let's see. Now, you know, we'll have to kind of zoom in. Well, I'm going to zoom in. You're going to have to look close at your page. Here's our slope field, and like this actually, well, it came from a calculator emulator, not Desmos, but it'll do the trick. And so I know both of these functions were sines. So no matter what, I should see some oscillation, which I kind of do here. Since there was only a single x or a single instance of x or a single instance of y, what I'm going to look at here is I'm going to look at the rows and the columns. So let's just pick a random column here. How about this one, going up and down? See how all the slopes are the same? That means this differential equation, the slope that it's giving you does not depend on y. So immediately I should be like, oh, it's the one that doesn't use y. So this one has to be dy dx equals sine of x cubed. But let's prove that. Let's look at it the other way. So I also want you to look at the rows here. So just pick a row. See all the lines, all the slope lines. See how they're changing as you go from left to right? There is some change here with x. Changing with x. So again, I know it has to be the one that has some dependence on x. Let's go look at the other one just to verify. So same thing. Let's either look at a column or a row. Let's do columns first. So you can see as you look down a column, see how the slope is changing? And likewise, if we look at a row, I see no change. So as x changes, the slope did not change. There's no dependence on x. So I know this one has to be the other one, the sine of y cubed. So that's it's not too bad when there's just an x or a y. You can figure it out kind of by looking at columns and rows and stuff like that. But if you have an x and a y, you're going to have to get a little more creative. So let's turn the page. Let's look at the last page. And in this one, I gave you 4 differential equations, which are all ratios. So x over y, y over x, then I threw some negatives in there. So there are just some general advice that I want you to think about if we're trying to identify which slope field is which. I want you can either think about like what values would make the slope positive or negative, would make positive or negative slope. You could ask yourself what values would make zero slope, what values or vertical. So these are typically what I'm looking for here. You could also pick like specific points if it really helps you and try and see what's going on. But that's kind of my last resort. Check specific points. So let's take a look at what we got here. Again, all of them x over y, y over x, negative, negative. So let's see. Looking at this first one, here's what I notice. I'm just kind of running through my questions here. Let's see. I'll just make some notes here in the middle. So equation A will equal 0 whenever y is 0, because that's the numerator. So if the numerator is 0, I'm going to have horizontal slope. So immediately I could look up at my 4 fields, 1, 2, 3, 4, and it looks like there are 2 that can be the candidate. It can be 1, because look, see here, as y is 0, those are all horizontal. And look at 3. Scroll down, computer, thank you. Again, all horizontal. Okay, so what else? We got to keep narrowing it down. The other thing, like I said, what would make positive? What would make negative? Well, how about dy dx? Actually, I should stick with the same color here. How about dy dx will be positive in quadrants 1 or 3. How do I know that? It's y over x. So if I have positive, quadrant 1 or 3. No. Oh, yeah. That'll work. So in quadrant 1, I have positive y's and positive x's, so that'll work. In quadrant 3, I have negative y's over negative x's. So let's check out our 2 candidates for our slope field. Okay, well, the top one here, those are all negative slopes in quadrant 1. Here are all positive slopes in quadrant 1. So field 3 is the only one which can meet both of these rules. So I know field number 3 matches up with differential equation A. Or we could say A matches up with field number 3, whichever way you want to notate. And if you looked at these rules in the other order, for example, if you asked yourself, where's it going to be positive? Okay, well, you would have started by saying like, hey, field 2 has the right positive slopes in the quadrants, but it would fail the first rule, and so it's no good. It doesn't matter what order you think about it. It's basically just a puzzle. Let's figure it out. So for B, come on, you. Bruh, I clicked it. I clicked it. Okay. For B, I'm going to do the same thing. Where's it going to be 0? This time, it's going to be 0 when x is 0. So that would be on the y-axis. Let's see. Well, that eliminates fields 1 and 3, and 3 because we already had an answer there. But so now our candidates are 2 and 4. I see 0 slopes all along the axes there. So then let's try and narrow it down. Let's again ask where's it going to be positive, where's it going to be negative. So how about it will be positive, again, just like last time. It's x over y, so I think it's going to be positive in quadrant 1 or, well, and. Actually, both of these should say and. Quadrant 3, because positive over positive or negative over negative. Well, here's some positive slopes, here's some positive slopes. Versus in 4, I have negative and negative, so it's no good. Looks like field number 2 matches up with equation B. Let's see. Gets a little more complex. I'm going to work down here for the third one. And I'll just recopy this slope. That way we can see it equals negative x over y. Oh, I got to clean this off too. Okay, so, okay, well, it's still going to be 0 when x is 0. 0 when x is 0, so that'll be helpful. You know, so again, our candidates are 2 and 4. Let's pretend we didn't already select number 2 for B. Then, okay, this, you could say where's going to be positive, where's going to be negative. This minus here is what's going to change that. So we could say dy dx will, you could say it'll be positive in quadrants 2 and 4. Or you could say it's going to be negative in quadrants 1 and 3. You know, whatever's easier for you. And you're going to find out, okay, the only thing that meets both of these rules is field number 4. So this goes with differential equation C, and that goes with number 4. Obviously, we could process and eliminate on the last one, but I want to run you through the logic one more time. So for D, the differential equation was negative y over x. Logic, okay, the slope is going to be 0 when y is 0. And the slope, let's just say, will be negative when it's in, again, quadrant 1 or 3. Or you could say it's positive in 2 and 4. Of course, there's only one choice left. It's the first one. You know, obviously, they're not always that simple. You know, you'll see x squareds, y squareds. You'll see some addition, subtraction. So like I said, you can also pick specific points. But hopefully that'll help you out with the logic and getting started. Okay, last one. Let's turn the page one more time here. Okay, all the slope fields. So this is a duplicate of field number 2 from the previous page. It's just blown up a little bit bigger. And our job is to draw a couple solutions, kind of like I did on the front page. Draw the solution to the differential equation through the point 0, 2. So if the function goes through the point 0, 2, which I'll put right here, what would the solution look like? Now, what some people do is they'll play like connect the dots with the lines. You don't necessarily have to follow the slope field lines exactly. Just remember they're kind of a general trend here. So I don't necessarily need to go straight through them, but I see it's increasing, it's increasing. Generally, it's pretty diagonal this way. And then if I go off to the left, same thing. So it's horizontal here, but eventually it's got to hook, oops. Eventually it's got to hook up a little bit. And with this, I do happen to be following the slope field pretty closely. That's also because there's 11 million slopes on here. If there's fewer slopes, it's a little harder to follow them. And our second task is to draw a different solution going through a different point. So this one's negative 3, 1, 2, 3, positive 1. So part B says, hey, what if it went through this point instead? What would the function, or what would the equation, the relation, look like then? Well, this slope's darn near vertical, but it looks like it's kind of hooking. If I was following the slopes around towards it, I think I'd kind of get a sideways parabola-ish sort of thing. See how, because it's vertical through the x-axis there, and it's pretty steep going into it, but then coming out, pretty similar to our first one up top. Kind of erased it. But yeah, we'd have to have something like that going on. Again, we don't know which one of these is the solution to the differential equation because it can depend. Remember, we said every antiderivative has that constant plus c. So the actual solution depends on what the c is. So that's what the slope fields are there for. We can still visualize, oh, this is what the function would look like if it went through this point. This is what it would look like if it went through this point. Even though it's not perfect, it's a pretty good approximation. As you'll see as we do more and more math, we are in the business of making some good approximations. Okay, great work today, guys. See you tomorrow.